So the primary conclusion was that we really have to go to all electric vehicles if we want to achieve our societal objectives. And we have two choices, battery EVs or fuel cell EVs. And what I want to do real quickly is look at the weight, volume, greenhouse gas emissions, and cost, comparing batteries and fuel cells. In terms of specific energy, in other words, the kilowatt hour or the watt hours per kilogram, an advanced lithium-ion battery, the goal is to get up to 150 watt-hours per kilogram of specific energy. A fuel cell, including the hydrogen tank, the battery, and the fuel cell system, as you can see, has much higher specific energy today than the advanced lithium-ion battery. And that translates into reduced weight for the vehicle. This is a plot of weight versus range. And if you look down here, around 80 or 90, maybe 100 miles range, a lithium-ion battery EV would have similar weight to a fuel cell vehicle. But if you want to go out to 250 to 300 miles range, then the lithium-ion battery vehicle will weigh much more than a fuel cell vehicle. Now, everybody knows that batteries are very heavy. What most people don't realize is that batteries take up a lot of space. Is that to accompany my talk? I didn't select that. Real sensitive site. In terms of watt-hours per liter, it turns out an advanced lithium-ion battery has coincidentally almost the same energy density as a 35 million Pascal hydrogen tank plus battery system plus fuel cell. So in terms of space on the vehicle, because the battery electric vehicle is heavier, you have to have more watt-hours, so the space is even greater. So for example, a fuel cell vehicle with 10,000 psi, 35 megapascal tanks, and 300 miles range would have about this much volume, let's say 200 liters. An advanced lithium-ion battery fuel cell vehicle would have about 3 times the volume on the vehicle. So batteries actually take up more space than fuel cells. In terms of cost, these are some data from the Cromer and Haywood report that I mentioned earlier. They estimated what the mass production cost would be for fuel cell vehicles in 2030 in mass production. They estimated a fuel cell vehicle would cost about $3,600 more than a regular car. Whereas a battery electric vehicle, they projected would cost about $10,200 more than a regular car. And you can see from this chart that plug-in hybrids, once you get above 20 to 30 miles all electric range, would also cost more than a fuel cell vehicle. I'm going to skip over some of this in the interest of time. So the advantages, fuel cells way less, take up less space, lower greenhouse gas emissions, lower cost, shorter refuel time. And I added a couple slides in here to emphasize this refueling time. And one anecdote I want to leave with you to emphasize how difficult it is to recharge batteries. Most people don't realize, but if you take a hose at your gasoline station and pump 14 gallons of gasoline into your car tank in 3 minutes, the power going through that hose is about 10 megawatts, 10 million watts of power is surging through that hose. If you look at hydrogen refueling, the NHA has analyzed 14,000 fuel cell vehicle refuelings as part of the DOE program. And the average power flow from the hydrogen going through a hydrogen line is about 1.6 megawatts. A home 120 volt, 20 amp circuit has a maximum power rating of about 1.9 kilowatts, which is 5,200 times slower than the gasoline hose, and about 850 times slower than the hydrogen hose. So this chart summarizes those data. And even if you go to 240 volts, 40 amp circuit at home, it's about 7.7 kilowatts. That's still 1,300 times slower than than gasoline refueling, and 210 times slower than hydrogen refueling. So it gives you a feeling for why it takes so long and so difficult to recharge batteries. I'm going to end with some cost estimates here. And here, we've changed things from what I presented last year. If you look at the 2008 National Research Council report on hydrogen, they estimated it would take about $8 billion to put in a hydrogen infrastructure system. But they assume that the government pays for 100% of that fueling infrastructure. Whereas what we've done now is said, long before all those hydrogen stations are out there, the hydrogen industry can make a profit selling hydrogen. So in other words, the government doesn't have to fund all of that infrastructure. As part of their normal business decisions, industry will make some of those investments. So the paradigm we're assuming here is that hydrogen would be made at the fueling station by reforming natural gas. So basically, we're making hydrogen by combining natural gas and water, taking advantage of the existing water distribution system and natural gas distribution system as kind of the backbone of the distributed hydrogen infrastructure system. So as a result, we can add hydrogen infrastructure station by station, fleet vehicle operator by fleet vehicle operator. Industry does not have to go along on hydrogen infrastructure. Here's an example of what our company made. This is what we call the HDM 10,000. Produces 10,000 standard cubic feet per hour of hydrogen, about 560 kilograms per day. This was developed under the DOE hydrogen program. And this system produces hydrogen at about $3.26 per kilogram. Today, if we add compression storage, that's another $4.83 per kilogram. The total cost is equivalent to about $2.04 per gallon of gasoline on a range equivalent basis. This is our first product at H2Gen. We take natural gas and water to make pure hydrogen. And here's the chemical formula. I threw this up here for a reason. This shows you that one molecule of methane produces 4 molecules of hydrogen. Half the hydrogen actually comes from water, which is one of the reasons that hydrogen in a fuel cell vehicle cuts greenhouse gas emissions by about 50%, because half the hydrogen comes from water without any carbon contributions. Here's an example of 4 of our units in the field. And this was our first unit actually using our system to refuel hydrogen cars. This is a Chevron station in Orlando, Florida. And our unit is actually, that's the exhaust from our unit right here behind this wall. And this chart just shows the cost of hydrogen from our units. Starting off with the smallest system, we can produce hydrogen at about $3.57 per gallon of gasoline on a range equivalent basis. And by the way, this is based on 2015 data using the EIA's 2010 annual energy outlook. And they're projecting the gasoline will cost $3.17 per gallon in 2015. If we use a bigger system, 170 kilogram per day production, we can produce hydrogen at about $2.80 per gallon of gasoline on a range equivalent basis. And if we mass produce bigger units, we get down as low as $1.34 per gallon of gasoline equivalent. So hydrogen today could be competitive with gasoline per mile traveled. Now here are the results from our new study on how much it costs for the hydrogen infrastructure. This shows the investments by industry and the investments by government. And we're projecting now, instead of $8 billion, industry would only be required to spend, government would only be required to spend $830 million. And no government support would be required after about 2023 of this model. The way we do that to make it lucrative for the hydrogen industry, we assume in the model that the price of hydrogen is set at such a level that industry can make a 25% internal rate of return on their capital investments. And this just shows the cash flow. Here's the expense of it, here's the hydrogen revenue. And the cash flow goes positive after 1 year. And as I say, they can make their hurdle rates with hydrogen pretty slow. Now we also have looked at the price of putting in public charging infrastructure for plug-in hybrids and battery electric vehicles.